This is a superconductor. It has zero electrical resistance. But is that really true? Well, today I'm going to attempt to measure the resistance of a superconductor as we cool it down and see if it actually drops to zero. Then I'll explain how it's possible that electrons in the superconducting state can never bump into an atom or even impurities, and they truly have zero resistance. I have a YBCO superconductor here. You can see that it looks really thick, but it's only a few millimeters thick. The back of it is just a casing that keeps it stable because this stuff is really brittle. And it also has some foam in there if you want to pour liquid nitrogen in here to keep it cool for longer. Now, measuring the resistance of a conductor, especially a superconductor, is a bit tricky. If I try to measure the resistance with my normal digital multimeter, you can see I just get zero. Now, copper has low resistance, but it's not zero. Normal digital multimeters like this one can't measure such small voltage drops, so they often just display zero resistance for good conductors. You have to use something called the 4-point method. In this case, what you do is set up one circuit to send a current through whatever you're measuring. Then you have another circuit that measures the voltage between the points on your sample. If the sample has resistance, the voltage will be higher at one electrode than the other. And using Ohm's law, which says the resistance is equal to the voltage divided by the current, you can calculate the resistance. So I'm getting around 1.6 milliohms here. So a very low resistance, but this is a good conductor here. But now let's compare it to a superconductor. As you can see, it drops and then suddenly it plummets to zero. So we're getting literally zero resistance across the probes here. This means that the voltage drop across these two electrodes is zero. We're running a known current through it and applying Ohm's law, but since the voltage is zero, the resistance is literally zero. Okay, it's now superconducting. Now this 4-point method is nice because it means we aren't measuring the resistance of the wires that are taking the measurement or the contact resistance of those wires on the superconductor. But let's watch what happens when I take it out now. Still superconducting. With it warming up, it's easier to see how it transitions out of its superconducting state and then rapidly increases in resistance. So the current in a superconductor will literally flow forever as long as it stays in its superconducting state. But how is that possible? There have to be some impurities or imperfections that make it not actually zero. Things like that don't happen in classical physics. But in quantum physics, they do. When electrons flow through a normal conductor, they sometimes bump into atoms in the positively charged lattice of metal atoms. This causes the atoms to wiggle a little bit, which we know as heat. But something odd happens when you cool down the atoms enough. As the electrons flow through the lattice, they pull on the positively charged atoms around them. To a neighboring electron, this area now looks positively charged, so it's actually attracted to the region where the other electron is. This causes the electrons to move together in pairs called Cooper pairs. These pairs of electrons act as though they're bonded together. Now, the physics of bonded electrons gets really interesting. Electrons are what we call fermions, which have a spin of 1/2. They obey the Pauli exclusion principle, which states that they can't be in the same quantum state at the same time in the same place. However, when two electrons bond together in a Cooper pair, one has a spin of up and the other has a spin of down. Combining together, it gives them a total spin of 0. This turns that pair into what's called a boson. Bosons, unlike fermions, don't obey the Pauli exclusion principle, so they can all occupy the same quantum state, just like photons in a laser. Remember how we can make photons coherent in a laser, all with the same wavelength and same phase? Well, a similar thing happens with the electrons in a superconductor now. They all get in phase with each other and occupy the same quantum state. So they no longer behave like individual point-like charged particles in the superconductor, but they act like one single wave in the superconductor now. And the electron wave has a larger wavelength than the spacing of the atoms in the superconductor. In this wave simulator, you can see that when we have a barrier that's on the same order of size as the wavelength, it scatters the wave. But when the wavelength is much bigger than the barrier, the wave just moves on undisturbed. This is what's happening in the superconductor. The energy to break up this wave is larger than the energy available in the atomic lattice. So the electron wave moves with no resistance, even though there are impurities in the superconductor. Now before we continue, just like Cooper pairs glide smoothly through a superconductor, having the right support in your life can help you glide through life's challenges. BetterHelp is the world's largest therapy service, and it's 100% online. With BetterHelp, you can tap into a network of over 30,000 licensed and experienced therapists who can help you with a wide range of issues. To get started, you just answer a few questions about your needs and preferences in therapy. That way, BetterHelp can match you with the right therapist from their network. You can communicate with your therapist in whichever way you feel comfortable, whether it's through messaging, phone, or video call. You can message your therapist anytime through the app or online and schedule live sessions when it's convenient for you. And if your therapist isn't the right fit for you for any reason, you can switch to a new one at no additional charge. With BetterHelp, you get the same professionalism and quality you expect from in-office therapy, but with a therapist that's custom picked for you, more scheduling flexibility at a more affordable price. So get 10% off your first month at betterhelp.com/actionlab, or you can click the link in the description. And thanks to BetterHelp for sponsoring this video. Now let's get back to our experiment. The magic of superconductors only happens because the electrons are surrounded by positive atoms. But what happens if you increase the current too much? So there's too many electrons. Well, with too many electrons, the shielding effect becomes insufficient, so they can no longer form Cooper pairs. When this happens, the electrons start acting like regular electrons again, bumping into atoms, and the material stops being a superconductor. But this phase transition only happens at really high currents. For example, I can put 10 amps through this superconductor and it still acts like a superconductor. 9.79 amps going through it right now. So we're nowhere near the saturation limit, which is crazy. That means I can hook up my car battery to it like this, and it can pump as much as 600 amps through it, and it'll still remain a superconductor. Still superconducting. Oh. The leads would melt long before any heat was generated in the superconductor material itself. If I generate a current in the superconductor by moving a large neodymium magnet over it, I should be able to see if the current is still there by measuring its magnetic field. If there were any resistance, the magnetic field would eventually die away. But you can see that no matter how long I wait, I can still detect the magnetic field on the superconductor. Now I should mention that the superconductor I'm using here is a high temperature superconductor. Normally superconductors require temperatures near absolute zero. So scientists believe there are additional mechanisms at play at these high temperature superconductors, because the temperature should be high enough to destroy Cooper pairs, but somehow they exist. But if we can better understand these mechanisms in the high temperature superconductors, we might be able to create a room temperature superconductor. And thanks for watching another episode of the Action Lab, and we'll see you next time.